Hello everyone, it's Mrs. McCready here, and today I'm going to take you through C9 crude oil and fuels for triple science. There are several topics we're going to cover today: hydrocarbons, fractional distillation, combustion of fuels, and cracking hydrocarbons. There's a Do Now activity for you up on the screen. Your teacher can pause the video here and come back to go through the answers. So they should have been some fairly straightforward mathematical calculations: percentages, ratio, and 1 mole calculation in question 3. So the first thing we're going to talk about today is what are hydrocarbons. We first need to talk about what crude oil is. Crude oil is a fossil fuel generated from the remains of plants and animals over millions of years, and it's drilled out from underneath the sea. You can see in this picture it's a thick black mixture, and that mixture contains hydrocarbons. Hydrocarbons are chemicals made of carbon and hydrogen only. They contain no other elements, only carbon and hydrogen. So all 4 of these diagrams are representing hydrocarbons. You can see there's different numbers of bonds in each molecule, but every molecule contains only carbon and hydrogen. So we need to know about a specific type of hydrocarbon called an alkane. Alkanes are a type of hydrocarbon that are saturated, and that means they only have single bonds. You can recognise those on a diagram by single lines joining the atoms together. Each line represents one single covalent bond or one shared pair of electrons. The structures and names of the first 4 alkanes you will need to learn. So this picture represents methane. It contains 1 carbon and 4 hydrogen atoms. Ethane contains 2 carbons and 6 hydrogen atoms. Propane, 3 carbons and 8 hydrogen atoms. And butane, 4 carbons and 10 hydrogen atoms. Notice a pattern in the formula for these alkanes. Alkanes belong to what we call a homologous series. That just means that they have the same general formula. So all 4 of these formula for the hydrocarbons on the left, methane, ethane, propane and butane, all fit the pattern CnH2n plus 2. So for n number of carbons, there are twice as many plus 2 hydrogen atoms. Let's look at propane as an example. Propane has 3 carbon atoms, so n equals 3 for propane. 2n plus 2, where n equals 3, will equal 8, and that fits our formula for propane. Shorter chain hydrocarbons, like the ones we have here, are more flammable, less viscous, and more volatile. They have a lower boiling point than longer chain hydrocarbons. These things make them much better fuels. They set on fire more easily, they are less thick or more runny, and they're more volatile and they can turn into a gas more easily. To make crude oil useful to us, we have to separate out that mixture that I showed you in the picture at the beginning. Crude oil contains fractions, and those fractions are just groups of hydrocarbons that have a similar chain length. And when I say chain length, I mean the number of carbon atoms in the molecule. We can separate out those fractions using a process called fractional distillation, and the fractional distillation column is shown in the diagram on the left-hand side. Crude oil is piped into the bottom of that column and heated to around 350 degrees. Most of the fractions will evaporate and start to rise up the column because they're now gases. The column is cooler as you move towards the top. So as they rise up the column, eventually the fraction will reach its boiling point. And at that point, it will condense back into a liquid and can be piped off the side. Remember, the boiling point of a substance is not only the point at which it turns from a liquid to a gas, but also the point at which it will turn from a gas back into a liquid if it's being cooled down. We're now going to talk about a process called cracking. These long chain hydrocarbons don't burn easily. They make very, very poor fuels. They're very thick, they're very viscous, and they don't set on fire easily. However, our demand as a society for fuel is much greater than the supply. So what we do is we solve that problem by using cracking, and cracking breaks down the longer chain hydrocarbons into shorter chain hydrocarbons. They make much better fuels, so they're more useful to us. This picture represents what's happening during cracking. Now the diagram is showing a hydrocarbon with 7 carbon atoms in as a long hydrocarbon. In reality, we wouldn't crack a hydrocarbon with only 7 carbon atoms. That's actually quite short. We would only crack hydrocarbons that are much bigger than that. But for the purposes of this illustration, we're assuming that that is a long hydrocarbon at the top of the diagram. During the process, we get 2 different products, at least 2 products. One will be an alkane, a shorter chain alkane, you can see that on the right, and the other one will be something called an alkene. We've not met alkenes before. The shorter chain hydrocarbon obviously makes a better fuel, so we can use that as a fuel to meet our demand. The alkene on the left can be used in the plastics industry, so they're also a useful byproduct. And we can test for these alkenes using bromine water. If you add bromine water to a substance that contains an alkene, the bromine water will turn colourless. Be careful here, don't write clear, it's already clear, bromine water, it's orange and clear, but if you add an alkene to it, it will turn colourless. Alkenes are different from alkanes in that they've got a double bond. You can see between the 2 carbon atoms in the middle of ethene, there are 2 lines representing a double covalent bond. Okay, so now we're just going to go through some quick questions. They're coming up on the screen. Your teacher can pause the video here, give you some time to answer these, and then come back to go through them in a moment. Okay, so to go through the answers to those quick questions, propane is the hydrocarbon with 3 carbon atoms. The formula for butane is C4H10. A hydrocarbon is a compound containing carbon and hydrogen only. Shorter chain hydrocarbons compared to longer chains are more flammable, less viscous, and more volatile or have a lower boiling point. The method of fractional distillation is described here. So you heat the crude oil, most of the fractions will evaporate and rise up the column. When they reach their boiling point, they will condense into liquid again and can be piped off the side. Cracking will produce shorter chain alkanes that meet our demand for fuels, and it also produces alkenes which are useful in the plastic industry. And finally, the test for alkenes is that bromine water will turn colourless. So we're now going to tackle some exam style questions. The first is up here on the board, so you can ask your teacher to pause the video here and come back to go through the answer in a moment. So for this question, you've not been given any data about diesel, heavy oil or kerosene, but they've told you enough in the question for you to be able to answer it. They've asked you to explain why diesel collects above heavy oil but below kerosene in the fractionating column. That tells you that diesel must have a lower boiling point than the heavy oil if it collects above it, but a higher boiling point than the kerosene because the column is colder at the top and hotter at the bottom. Bitumen is a fraction with a boiling point range of 400 to 450 degrees. 2 reasons that it wouldn't be used as a fuel are that it's too viscous, not flammable, or that its boiling point is too high or it's not volatile enough to make a good fuel. Here's the second of our exam style questions. Again, your teacher will pause the video here and come back for the answers in a moment. The formula for methane is CH4. Carbon monoxide is produced when methane is burned when we have incomplete combustion. The reason we get incomplete combustion is if there's limited oxygen, and the danger of carbon monoxide production is that it is toxic. You must be specific there. You must either say toxic or poisonous. Don't use generic words like harmful. The balanced equation is shown at the bottom here, so you should be producing carbon monoxide and water as your 2 products. The third and final exam style question is on the board. Again, your teacher can pause the video here and review the answer with you in a minute. The reason that large hydrocarbon molecules are cracked is to produce those shorter chain hydrocarbons which are in greater demand because they make better fuels. The equation can be completed by adding C3H6 in that gap. That's the formula for an alkene, but it also makes sure that the numbers of carbon and hydrogen atoms on the left-hand side of the arrow and the right-hand side of the arrow are the same, because 12 plus 3 equals 15, and 26 plus 6 equals 32. So that brings us to the end of this review session of C9 Crude Oil and Fuels for Triple Science. Really well done. We've covered 4 topics today: hydrocarbons, fractional distillation, combustion of fuels, and cracking hydrocarbons. If there's anything in the video that you'd like to see again, ask your teacher and they can go back to that particular section. Otherwise, you can spend any time you have left during this lesson reviewing and recapping that content.